last major rule for derivatives has a much better name than the product and the quotient rule, because it has a word that's probably never come, I don't know if it's ever come up in math. The chain rule. And I don't know why it's called the chain rule, but it's a cooler name than just mathematical words of product and quotient. So the chain rule happens when you have one function inside of another function. So that could look like this. 3x plus 2 is inside something getting cubed. In function notation, I would say that what I've underlined here in green is probably what you're used to for a function inside of another function. Here, g of x is inside of f of x. And if you had something like you had to do this, this would mean you would first plug the value of 3 into the function g. Whatever answer you get then gets plugged into f. And then you would get an answer in the end. So this is g is inside of f of x. Okay? This is not as easy to see in this notation. But that's another notation for the composition of functions. It's kind of like smaller than an O, a little bit bigger than a degree sign. I don't know what you would. It's not a little zero, but I always joke that I don't like this notation because it's unclear and it spells fog. I say it's foggy because it kind of spells foggy. So whenever I see this notation, I would change it to the other notation as far as composition of functions. And what we have to get really good at is just recognition when something is inside of something else. And the first ones with powers, I think, are really easy. Because here you have a 3x plus 2, and it's inside something getting cubed. So if we call the inside function 3x plus 2, then your outside function is x cubed. Does this make sense? That if I plugged in 3x plus 2 into f of x, the x would get replaced with 3x plus 2, and I would have 3x plus 2 cubed. Right now, if we wanted to find the derivative of this, our only option would be to multiply out 3x plus 2 times 3x plus 2 times 3x plus 2, which wouldn't be very much fun, but is doable. And then you would get, for example, we'll do the easy parts. 3x times 3x times 3x. You would start off with having a 27x cubed. You would have a bunch of things in the end, and then finally 2 times 2 times 2. You'd get 8. And then that derivative would be easy. So we could do this. We could multiply this up. But if there was a shortcut that we didn't have to multiply that out, that would sure be nice. So now what we're going to do is we are going to imagine we multiplied this out, we got an answer, then we decided to factor that answer to see what it looked like, and we end up getting the following. Yeah, I'll even cheat and write it like this one. Technically, when you factored it, you would have got a 9. 3 times 3 is 9, but I'll write it this way for cheating purposes. So you'd be like, oh, okay. Do you see a little bit of the product rule happening? Right? But you're like, oh, I bring the 3 out, subtract 1 from the exponent. But I've got an extra 3 there. So I'm not quite sure where that comes from. So what I do is I do a bunch more. Okay? Now you have to have a little bit of pretending, because if I tried to honestly tell you that I did these, you could call me out as a liar. Because there's no way I multiplied 3x squared minus 7 to the 40 out and got 41 terms. Then did the derivative, which would reduce it to 40 terms, and then decided to factor that using synthetic division and the factor theorem, and come up with, oh, look how nice it factored. Okay? So I would be lying. But this would have been, initially, before someone knew the chain rule, this is what they would have done. They would have been like, hey, this is cool. That's a neat pattern. This is interesting. And once you notice a pattern that's interesting, then you go and try to prove it. And sometimes when you prove things, then you get disappointed. I'll tell you a story about that after we go through these. Okay, so first pattern. Do you notice with the outside function? So I'm going to start talking about an inside function and an outside function, and that language is going to help us understand the chain rule. So when we have composition of functions, one function's inside of the other. So the one that's inside, I call the inside function. Makes sense. But I call the other one the outside function. So in all of these, the outside function is the power. And what's inside the brackets is our inside function. So the first pattern that I hope that you're noticing is that your outside function, which is a power, is following the power rule nicely, where 5 comes out in front, subtract 1 from the exponent. The 40 comes out in front, subtract 1 from the exponent. And that would be your regular power rule if you just had a nice x inside. But we have more than just a nice x inside. So when we did the derivative, we find out there's also, well, in this one there's a 2 outside. In this one there's a 6x outside. In this one there's a 4x cubed minus 1 outside. And on this one there's a 5x to the 4 on the outside. So then we have to figure out, well, where did that extra number come from? Can you see a pattern for those numbers? Rohan, where do you think the 2 comes from? No idea. What about the 6x?
Just 2 multiplied by 3.
Okay, so we got a derivative of this part here. And then there's a 7s, but I don't know what happened to that. Okay? Does that help explain this one?
Yeah, the 2.
The derivative of the 2,
Yes.
and the 3 went away. In fact, you could think of this 2 as just the derivative of the inside. Does that work for this one? Yes. Does it work for this one? Even when you have more things. What's the derivative of the inside? 4x cubed minus 1, 4x cubed minus 1. So again, the reason I gave you time in the previous classes to really practice and practice and practice is because we need to know the other derivative rules really well in order to see the patterns in the next rule. So what we have is the chain rule from the pattern. It looks like we did the derivative of the outside function and kept the inside function the same. Right? So we just did the derivative of the outside without worrying about the inside. The inside stayed the same. And then we multiplied by the derivative of the outside function. And that happened every single time. Derivative of the outside function, 40, subtract 1, keep the inside the same, multiplied by the derivative of the inside. So we're starting to notice in a lot of our special rules, product rule, quotient rule, and now chain rule, there's always something that temporarily stays the same. Something stays the same, and this is actually quite hard for people mathematically, because mathematically you want to do something. You want to change something, and we're not very good at having patience. And we have to have patience because the inside stays the same, and you'll be wanting to do the derivative of it too soon. Then you multiply by the derivative. So what does this look like as the chain rule? Yeah. The actual format of the chain rule, we probably won't use very much because it's actually quite terrible. But we'll look at it formally, but you're going to find out that this way that we talked about it, derivative of the outside function, keep the inside the same, multiply by the derivative of the inside function, is going to be really easy for us. Actually using the formula is kind of hard, okay? If y is a function of u, I shouldn't have used u, because then I have to say f u, which is inappropriate. And u is a function of x, meaning that u is g of x. In other words, y equals f of g of x. Then the derivative in Leibniz notation would be the derivative of y with respect to u, which means you keep u the same. Then you multiply by the derivative of the inside function, which is du dx. But again, the words, and maybe, I don't know if you want to write them down. Because this, take the derivative of the outside function, keep the inside the same, then multiply by the derivative of the inside function. Technically, that's what this says in Leibniz notation, but it's hard to read that. This is easier to see. Here is, if you have a function inside a function, you keep, here's the derivative of the outside function. Was it too quick? Do you need to go back?
No, you say that and then after that.
Here, no problem. I get excited about the next slide. This. So in Newton's notation, a little bit easier to see. Here's the derivative of the outside function. The inside stayed the same. Then you multiply by the derivative of the inside function. Okay. Here is, I don't even know if I should show you. It's important that we see this because later on we undo this with integration. But we never ever use this method for the chain rule because it's too tedious, confusing, and prone to mistakes when we can do it a much easier way. Okay? So the much easier way that you are going to do for this question, so we'll do it first so that we can see the easier way, and if you choose to ignore the rest of what I tell you, that's up to you. Okay? The derivative of this would be, my outside function is the power of 5. I do the derivative of my outside function, which means the 5 comes out in front, the 4, you reduce 1 by the exponent, and I kept the inside the same. And then I multiply by the derivative of the inside function, which is 3. That's how we're going to do the chain rule. One step. If you remember those words, easy, no problems. And even when we get into more complicated ones, if you remember those steps, you're still able to do it. Okay? If we go to this method, we get into the more complicated ones, I guarantee we will make mistakes and not be able to do it at all. But it is important to see. So what you do is you choose your inside function and label it u. Maybe this is why I chose u, because I like this method so much that I get to use the fu part in it over and over again. Okay, that's probably why. So we make the u our inside function, which is done here already. Then you can find dy du, and you can find du dx. So if I make u my inside function, well, then du dx, the derivative, is just 3. That part's easy. If I make u the inside function, I can also rewrite the original function as u to the 5, and then dy du, right, because we now have a different variable. Well, this is just a simple formula. So we can now say, I know dy du, we have a space bar here, 5u to the 4. I know du dx, that's 3. According to the chain rule, then dy dx is equal to dy du, which is 5u to the 4, times by du dx, which is 3. And then I would have to go back and substitute what was u? Well, u was 3x plus 6. Oh, we got the same answer in a lot more time than what we had from before. So we can see why we maybe would just like to do the words of derivative of the outside function, keep the inside function the same, then multiply by the derivative of the inside function, because you could write your answer all at once without doing complicated substitutions. And especially when, and it's going to happen, you're going to have chain rules mixed into product rules, mixed into quotient rules that get very big and very complicated, and any time that you'd have to step away and do a bunch of substitutions, you're going to lose your place and make a mistake. So it is important that we can do it directly, but this is the rule for how it works. We want to find the gradient function, that's another word for the derivative, for this equation. And what we're going to do for this equation is we see a quotient. So you could do a quotient rule, but on the bottom of your quotient rule, you see that you have a function inside of a function. So sometimes we will want to decide, do I want to do a quotient rule with a chain rule embedded in it? Or do I want to use my exponent rules to bring that 4 to the top, and then I have just a chain rule? So I still have the x squared plus x inside of the function. It's inside of the x to the minus 4. The chain rule would say, do the derivative of your outside function. That's the power of -4. What does that look like? Well, the -4 would come out in front. I would subtract 1 from the exponent and keep the inside the same. Then the chain rule says after you've done the derivative of the outside function and kept the inside the same, you then multiply by the derivative of the inside function. That'll be your 2x plus 1. And we're done. You could do this, though, with a quotient rule as well. So, just for fun, we could look at that. What would this be if I did the quotient rule? Well, the quotient rule says keep the bottom the same. So that would be x squared plus x to the 4 multiplied by the derivative of the top. And the derivative of 3 is 0. Minus, keep the top the same, so that'll be my 3, multiplied by the derivative of the bottom. And the derivative of the bottom is a chain rule. So the chain rule says, do the derivative of my outside function, so I subtract 1 from the exponent, keep the inside the same, multiply by the derivative of the inside function over the bottom square. Squaring the power of 4 would be a power of 8. So you can see that this 0 would make this go away. You see you have a minus 3 times a 4, that would match up with that minus 12. Do you see on the top of your fraction that we have, that we have the 2x plus 1 that matches up with the 2x plus 1? And as far as our x squared plus x, in the top one we had a minus 5. Can you see on the bottom one, if you simplified, because you have the power of 3 in your numerator, power of 8 in your denominator, they would cancel out. You would be left with a power of 5 in your denominator. And a 5 in your denominator would be like the minus 5 in the top. So both the blue answer and the black answer are perfectly fine and correct. Just like we did when we had our roots in a regular power rule, we're going to do the same thing with a chain rule. We're going to take the time to rewrite this as a 1/5. Then recognizing you have a function inside of another function. Your 3x squared plus 7x is inside the 1/5. So for our derivative, we would do the derivative of the outside functions. The 1/5 would come out in front. I would subtract 1 from the exponent. I would keep the inside the same. And then multiply by the derivative of the inside function. Perfect. And again, even though we're getting these complicated rules, the answer is written in one step. So is calculus the most complicated one-step questions you do? Probably. I'm going to rewrite this one. The square root would be a half. The half is in my denominator. I'll move it up to a -1. And now I have a function inside of a function, but I don't have to worry about the quotient rule. Usually if you have a quotient with just a constant or single number on the top, it makes sense to use your exponent rules so you don't have to use the quotient rule. Oh, okay. So our derivative of the outside, bring the negative 1/2 out in front, subtract 1 from the exponent, keep the inside the same, then multiply by the derivative of the inside. And one can only imagine what the definition of the derivative would look like in this one. So I guess I want you to appreciate how fast we're doing these, because I think you're already forgetting those super long questions we had to do with the definition of the derivative. You still have to know how to do that. But then, I don't know, I have the answer. There's something enjoyable about thinking about how hard that would be with the definition, and then just going, haha, I don't have to do it. And then feeling good about the short. Right? And then when your friends are in university and they're in the first unit of calculus and they haven't learned the shortcuts, you should like say, hey, try this one. That's kind of neat. Would be kind of enjoyable being an executive. You can tell them afterwards that you did this so that they really appreciate the chain rule. It was for reasons of appreciation. Work backwards. Can you figure out what was here originally? Yes. So we had a chain rule happen because we have the outside function, the inside stayed the same, and then the derivative of the inside was afterwards. So there is and now we start to have some fun. We've been having fun, but we combine our rules and see if our brains can handle it. It is truly a measure of, can I handle these rules when more than one of them happen? And it's challenging. So here we have, well, first of all, I see the square root, so I'm going to take some time to change that to a half. And I notice a multiplication here. So I have a product. I can't simplify that easily because of the exponent of the half. So we can't actually multiply this out even if we wanted to. So I have a product rule, but in my second thing in the product rule, there is a function inside of another function. So we have to go through the words of our product rule. Our product rule says, keep one the same, multiply by the derivative of the second one. And when I multiply by the derivative of the second one, my brain says there's a chain rule. So now I have to, in the middle of my product rule, go through my chain rule. So my chain rule. 1 second. We're right. Our brains are. Okay. Bring the 1/2 in front. Subtract 1 from the exponent. Multiply by the derivative of the inside function. So my brain just went through the chain rule steps, and now I have to take a step back and say, where was I in the product rule? In the product rule, I had kept the first one the same, did the derivative of the second one, so now I have to add, keep the second one the same, multiply by the derivative of the first one. So what do we notice? Our quotient rule, product rule, and chain rule aren't long. They're like involved things. And when they get combined, you have to keep track of where you are in those rules. So what did I do here to recap? My product rule is keep one the same, derivative of the second, keep the second the same, derivative of the first. You can check it afterwards. In my derivatives, this derivative of the second one was easy, but the first one, when I did the derivative of that second function, I had a chain rule. So I have to double check my chain rule. Chain rule says I bring the 1/2 in front, subtracted 1 from the exponent, kept the inside the same, multiplied by the derivative of the inside function. Whew. So again, I'm going to take some time to change that square root. We have chain rules for the top and for the bottom. Yeah.
Do we have to simplify that?
No. We can, I mean, when you, yeah, there will be some questions, and when you do your questions out of your textbook, they will simplify them a little bit. This one's actually quite interesting to see what the textbook would have as their answer. The textbook would have the, do you want us to have some fun simplifying? No? Okay, we'll leave this. The textbook would end up with an answer with a square root, because this is a square root, right? And a negative would put it on the bottom. They would actually take that square root, write it on the bottom. Then they would say, well, you can't leave things as adding two things separately. We should get a common denominator. So they would get a common denominator and combine this all as one fraction. Very good algebra skills. We'll leave it for now. Lots of them you will not have to simplify. We have a quotient rule with two chain rules inside. Okay? So we start with our quotient rule steps. Which one do we keep the same? Top or the bottom? Keep the bottom the same. 1 minus 8x squared cubed, multiplied by the derivative of the top. The top is a chain rule because there's a 5x inside of the half. So when I multiply by the derivative of the top, the half would come out in front, keep the inside the same, subtract 1 from the exponent, multiplied by the derivative of the inside. Now where am I in my quotient rule? In my quotient rule, I now subtract, I keep the top the same, and multiply by the derivative of the bottom. And the bottom is a chain rule. So the chain rule says outside function, subtract 1 from the exponent, keep the inside the same, multiplied by the derivative. Oops. Sorry, keep the inside the same, multiplied by the derivative of the inside, over, what do we do on the bottom? Square the bottom, so the cube will become a 6. Try the next one, double chain rule with product rule on your own. Just so that we're all the same, let's rewrite first one as an x to the minus 1 inside of a third. Does that make sense? So I am going to just make that an x to the negative 1/3. So we only have one chain rule now, which is kind of nice. Because the x to the negative 1/3 isn't going to be a chain. It's just an x. So how did we do? Oh, sorry, didn't take space, so I can start over here. F prime of x equals, keep one the same. Multiply by the derivative of the second one. Derivative of the second one, bring the negative 1/3 out in front, subtract 1 from the exponent, plus, keep the second one the same. Derivative of the first one, and the first one is a chain rule. Chain rule says derivative of the outside function, which means the 4 comes out in front, subtract 1 from the exponent, keep the inside the same, multiplied by the derivative of the inside function. So the idea being, starting to notice, we really need to have these rules well memorized and set in our heads because we're going to be doing them meshed together. So we have to take, where was I in my product rule? Lots of things to think about. So you might have to stop, go back, say, where was I? What did I just do? Follow through on your rules as you're going along. Okay, another one for you to try. All right, and there's the answer so you can check how you did. Did you change the square root to a half? Did you see that there was a product rule? Because you had x times by something else, so I kept the first the same, derivative of the second one. Then, when evaluating it, because it says find the slope or the gradient of the tangent at x equals -4, I changed all of my halves back to square roots. For mental math, I felt that that would be easier. Because when I plug in -4, I get square roots of 9.